Hello, everybody. Really nice to meet you. I hope you're not starving yet. I'll try to speed up a bit. Yes, welcome everyone to OWASP and to my talk about securing web apps with modern platform security features. Today's talk will be about a couple new features in the web platform that you can actually use to protect your applications and users from common web vulnerabilities. And my name is Lukas Weichselbaum. I'm an information security engineer at Google. I work in the Zurich office, and my team is focusing on improving product security by targeting proactive projects with the aim of mitigating whole classes of bugs. And today, I will split the talk in two sections. First, a very quick run through common web security flaws, not like explaining what they are, but more like looking at VRP data and seeing which ones are common and try to categorize them and map them to web platform security features. And in the second part, we'll talk about these web platform security features that are, some of them are super new actually. We probably not even have heard about them yet, but it would be super cool to start a discussion about them maybe later outside as well. So let's start with the security flaws. Google has a VRP program I think for over 8 years now, and it's not only a great source for finding bugs and fixing them, but it also allows us to actually look at the root causes and identify new classes of bugs and kind of try to get a feeling of trends within these bug classes, right? So there's thousands of bugs submitted every year, and in particular, the web application bugs are out of interest for us. If you look at the left side of the chart, you'll see that less than the half is non-web bugs, like server-side misconfiguration or Android applications. We'll not focus about these today. We'll focus on the right side of the chart, which is slightly more than 50%, and these are web endemic bugs, right? Of course, cross-site scripting is a big offender in this space, right? And it's still around. And then there's other things like cross-site request forgery, click checking, and other web bugs, which we'll cover in a little bit more detail in the later sections. So the first big category is, of course, injection bugs, right? And I'm not going into detail about what cross-site scripting is because I assume most of you know. The only thing I want to mention is the second type of cross-site scripting, like DOM-based XSS, is actually becoming more relevant these days because more and more code is moving from the server side to the client side, and it's actually quite easy for developers to introduce DOM-based XSS by accident, and it's on the other hand very hard for security reviewers to spot these bugs in code reviews, right? So that's cross-site scripting, and part of the talk will be about to prevent and mitigate these bugs. But the larger part of the talk will be about insufficient isolation and new web platform features that help you to address this category. So the classical example here is cross-site request forgery, right? And I'm not going into the detail how that works, but the very important feature of it is that the server has not enough information to actually tell apart a request from the site's origin compared to a request that originates from a evil.com site, right? Like from a random origin on the internet. So evil.com can put a form that looks exactly the same on their site and have JavaScript submit that form. And for the server, since the browser will append cookies to both requests, these two requests look exactly the same, right? And one of the web platform mechanisms we want to present today is exactly about this. So, and cross-site request forgery is just one of these isolation-related issues. There's also cross-site leaks, timing attacks, and lately also a couple of new classes of vulnerabilities that have popped up that also fall into this category of insufficient isolation in the browser platform. The most known new one is probably Spectre, which is a microarchitectural issue. And yes, so You could say, like, this chart looks great, but it's maybe a bit Google biased. And you're right, it's the data from our VRP, so it has a Google bias. But if you look at other VRP data, for example, from HackerOne, you will see that they actually see similar trends when it comes to cross-site scripting, cross-site request forgery, et cetera, right? So this is still a big issue for the industry. And also our friends at Mozilla report similar statistics about these vulnerabilities. So what we want to do now is to address these classes of bugs in the web platform, in the browser, right? And there's a couple of new things that have been already launched and are coming up soon, which I want to show you today. And as I mentioned, we basically have divided this up into two categories, isolation mechanisms and injection defenses in the browser. And in this talk at OWASP, I'll mostly focus on the isolation part, mostly because of timing reasons, but if you want to see the full-fledged talk, you can also get the recording from Google I/O. And so let's start with isolation. So you might ask, why do we need isolation? The answer to that is that because of certain issues in the way the browsers isolate different origins from each other, there is vulnerabilities like cross-site request forgery, cross-site script inclusion, click checking, web timing attacks, Spectre. They all fall into that category. And in particular into this subcategory of attacks on resources. So attacks on resources are usually caused by the fact that any site on the internet can load a resource from your server, and your server cannot tell apart that resource load from a resource load originating from your own site, right? So there's attacks on resources, and a second subcategory of isolation-related attacks are attacks on Windows, more specifically on attacks based on like having a reference to a window of a different origin. So the web is very open when it comes to that regard. Any site on the internet can open a new window and navigate that window to your document, right, or to your domain. And that per se is fine, but by doing so, that site will still have a reference, a window reference to your window. And because of that window reference, you can do a couple of things that are may or may not be surprising to you, right? For example, you can count frames in your site. The original window can also do some other, side channel attacks, often used in cross-site search. The new cross-site search attacks, they can do like tab nabbing, etc. And especially for browsers like Firefox that don't have a full site isolation implemented yet, it also means that they cannot put the new window document in a separate process and protect you from Spectre because of this window reference. So the second platform mechanism I will show in a bit will be about that particular feature. But before we get into that, a super quick review on origins and sites. I assume most of you know what same origin means, but maybe not everyone knows about the concept of same site. So same origin is basically the tuple of scheme, host, and port. And whenever two URLs have the same values in this tuple, they're considered same origin. For example, www.google.com/foo is same origin to www.google.com/bar. Same site is similar but different in the sense that neighboring subdomains on the same registerable domain would be considered same site. So mail.google.com and photos.google.com would be considered same site, but not same origin. And basically everything else is just cross-site. And this distinction is very important because based on that, the browser enforces different isolation mechanisms on your site, right? And with that, we come to the first new web platform feature to address the resource isolation problem we showed you on the first slide. And it's actually quite simple. It is just 3 new request headers set by the browser that basically give the server a chance to reason about the context and the source of an HTTP request. So implementation-wise, it's really simple. It's just 3 request headers. The first one is sec fetch site. This is sent by the browser for every request, and it basically just indicates the source of a request, right? It just tells the server this request was made like cross-site, or for example, this request came from your own site from the same origin. And that is extremely helpful for the server because suddenly in the cross-site request filtering case, the server can actually reason and say, oh wow, this request came from evil.com and not from mysite.com. So I may just want to block it or strip cookies or do whatever with it, right? You can have custom logic on the server dealing with that information. The second header is sec fetch mode, indicating the type of the request. And most simply put, this means this header indicates if this was like a resource load or if it was a navigation. And we'll see in a second that this information is also quite handy to protect the server side against a couple of web vulnerabilities. And the last header is sec fetch user, which basically informs the server if the navigation was caused as a direct consequence of a user interaction, like a click or a key press, or if it was, JavaScript based or something else. So let's look at a super simple example for this. On the top, you see a same origin resource load. Site.example loads a file from site.example server. And by that, the browser sends an additional request header called sec fetch site with the value same origin, because it's a same origin request. And the server can say, well, same origin requests are allowed. That's perfectly fine. The example below is actually a cross-site request. Evil.com requests something from site.example, and by doing so, the user's browser will basically indicate on the request that this request was made cross-site, because the host and of the request and the actual source don't match. So that's still very simple and simple information, but you can actually use these building blocks to build some quite powerful server-side logic to protect web applications against a couple of common web application security flaws. And that example here is a little bit simplified, but this basically prevents a couple of resource isolation related issues, and most commonly known, like it will prevent cross-site request forgery, cross-site script inclusion, click checking, and similar issues, right? The logic is actually easy. The first condition just checks if the sec fetch header, request header is available, because if not, it's a browser that does not support this and will just allow the request because we don't want to break the site for users on all the browsers, for example. But eventually, when all the browsers will support the feature, the security will also be available to more users. The second condition is basically there to ensure that all same site or same origin requests are allowed to proceed, right? So if your site makes a request for JavaScript or navigation or whatever, right, the server will just normally respond to it because it's the same origin or same site navigation. And the third one basically ensures that cross-site navigation, top-level navigation, is also allowed. If you don't have the third condition, your site will basically be siloed in the internet and no one will be able to link to your site, right? There's some use cases for that as well, but in the normal case, you still want other places to be able to link to your site. So you still would allow top-level navigation, even if it happens cross-origin. So everything else is blocked. What that means, for example, if you take the XSSI example, if evil.com loads a JavaScript from your site and the browser sends cookies with that request, right? Your server will basically block that request because it's a cross-origin resource load and you did not explicitly allow this here. So there's actually many more things you can do with fetch metadata, but this is like a trivial example how to address resource isolation related issues with that mechanism. Usually you would roll out a fetch metadata based protection in the form of a middleware on the server side. You would start monitoring the blocked requests, not actually blocking them, and review all the requests that actually got blocked, right? Because potentially your application has endpoints that are meant for cross-origin communication. For example, if you have a course endpoint that is meant for cross-origin communication, and you would probably want to whitelist that endpoint from that logic to still allow that, right? And if you have done that, you would switch to enforcement mode and actually, for example, block all requests that don't fulfill this criteria. Or you can also do something custom, like stripping cookies, redirecting to the entry site, or doing other things, right? And also very important to note here, you would also have to set a vary header for segfetch site and segfetch mode. And this also has a very nice side effect that browsers will basically be forced to have a per origin cache compared to having a cache for all sites, right? And implicitly by that, you will prevent a couple of excess search related issues just by ensuring that the stuff is not cached across origins. And so fetch metadata is shipping in Chrome in the next version in 76, but you can already play with it by enabling the experimental web platform features flag. And yes, there's also already 2 projects on GitHub that provide a proof of concept implementation for resource isolation based middleware using fetch metadata. Give it a try, give us feedback, and super curious to hear what you think about the approach. And with that, I'm switching to the next feature, new feature, which is a cross-origin opener policy. And that in particular addresses the isolation issues related to window references, the second category we had on the slides before. So what is this about? As we already said at the beginning, any site on the internet can open your site in a new window and have a reference to that window. And with that reference, they can send post messages, they can count frames, they maybe leverage other side channels to, learn about something about your site. For example, they could find out if the user is logged in or not based on some things. And they can also navigate your site away to an arbitrary other site. And there's a very easy way to prevent that, and that's the cross-origin opener policy response header. You basically can set this header to same origin or same site, and by that, any cross-site page that opens your window will still be able to open the window, right? But it will not have the reference anymore, and by that, it will not be able to navigate your window and your site anymore. And especially nice, the same site value can be used if you, for example, have a couple of subdomains and they, communicate through post message, and you would still want to allow that, right? So this response header is quite new. It's already implemented in Firefox nightly, so you can try it. Chrome is working on it, but as of now, I think there's nothing implemented yet, but we'll hope it will come soon. And another very nice side effect of setting this response header is that browsers like Firefox, who don't have full site isolation to protect against Spectre, will be able to put the open window or the other domain in a different browsing context group, which means the browser will be able to separate the domains, the origins with different processes, right? And by that, protecting against Spectre-like attacks. So especially for Firefox users, this header would be quite interesting as well, because I think it will take some more time for Firefox to actually natively implement full site isolation. Yes, and with that, I will do a couple more slides on injection defenses. There is CSP, which you can use to protect against stored and reflected XSS, and partially DOM-based XSS. It was a long ride for CSP. I don't know, I guess some of you have seen CSP and worked with CSP before, and you have seen policies like that. It's not great. This type of policies are super bad because they are trivially bypassable, they're incredibly hard to maintain without breaking things, and yeah, they're just not really worth your time, right? What we would suggest instead is using a CSP based on nonces, because it has two critical advantages. And the first is that this policy does not need configuration per endpoint or per site. As a matter of fact, we use almost the same policy across all Google applications. And the second thing is it's not susceptible to the whitelist-based CSP bypasses, which the previous policy, the whitelist-based policy would be. So we actually use this type of policy on over 60% of all outgoing Google text HTML traffic, and I think on over 100 domains. And it was quite effective. Just in the last 12 months, it actually blocked 20 high-risk XSS bugs. And for us, that's very valuable time to actually fix the bugs and preventing them from being exploited. So I'm not going into the details how to roll out the CSP based on nonces, but there is a nice write-up on csp.withgoogle.com that gives you a step-by-step guide on how to do that. And I also strongly recommend, if you already have a CSP or if you diverge from the template, to actually use the CSP evaluator, because it actually is very useful to spot common bypasses in a policy that make it completely bypassable. So whenever you have a red exclamation mark in your policy, you might want to do something about it or just delete the policy. And yeah, the TLDR is, the nice thing is like always the same, except of the nonce, which has to change on error response. It's definitely better than whitelist-based CSP, and it's a good mitigation against stored and reflected XSS. And with the new CSP-free strict dynamic keyword, you actually can use the nonce-based CSP even in the case when you'll have third-party JavaScript code that loads resources, right? Like payment integration, using JavaScript from CDNs or widgets, right? In that case, earlier you couldn't use a nonce-only CSP, but with strict dynamic, you can also now use a nonce-based CSP in these cases. And here is a small pitch for another talk. There's also trusted types coming up in the web platform, and it's an amazing new feature, especially extremely well suited for preventing it against DOM-based XSS. And there's a talk by Christoph Kotovic and Mike Samuel, I think after the lunch break. And of course, I don't want to steal their thunder, right? So you should. Sorry? Whole C130. So you should totally check that out. It's one of my favorite new web platform features. And what's really nice about it is it also plays very well with the classical CSP. So you can set a single policy with trusted types and nonces, and together they are very effective in actually preventing and mitigating the vast majority of XSS issues, right? So that should be your 2019 goal. And yes, with that, I will wrap up. And basically you can now wake up again. I put everything on a single slide. You can take a photo and pretend you know everything about these features now. The TLDR is that you can use CSP3 for reflected and stored XSS, trusted types for DOM-based XSS, fetch metadata request header to protect against isolation issues that are based on resource loads, and you can use cross-origin opener policy to protect your window references from tampering. And with that, I wanted to thank you for being here today. The slides are online as well, and I put some of the links also here, just in case you were not able to note them down previously. And I will hang around a bit longer in case you have questions. And, sorry? Oh, we even have some time for questions if there are some. So, yeah. Sure.
So until the slide that you have, that it's clickable and it was a GET request.
Clickable, was it a fetch metadata?
Yes.
1 second.
In the beginning.
So, was it the...
Yeah, that slide, you just passed it.
This one?
Next one? Yeah.
Yes.
So the third condition, why does it have to be a GET? What if it was a post?
So this is mostly for cross-site request forgery protection. So a classical cross-site request forgery case is a post